All right, so this is our second lecture on Chapter 8, and it'll be our second and final lecture. And we covered a lot of ground already, hydrodynamic considerations, talking about the use of M. Hey, what does that U subscript M indicate? The mean velocity. We also talked about thermal considerations, T sub M, the mean temperature of the flowing fluid in a duct or pipe. We talked about the velocity profile if it is laminar, or the velocity profile if it's turbulent, a good review of fluid mechanics, talking also about the Reynolds number based on the diameter of the pipe. So the 2300 is the critical Reynolds number, below laminar, above turbulent. Talked about how to get that friction factor. The friction factor is given by a single equation, an easy to remember equation. Do you remember that equation? 64 divided by that Reynolds number. And then what about for the turbulent case? What's the friction factor? How do I find that? Yeah, use the Moody chart. So use the Moody chart. Or you can use, there's correlations out there. Churchill equation, it's not in the textbook, but it's a great correlation. And there's also Blasius correlation. Some of them are restricted in this range of Reynolds number, turbulent flow only, or smooth pipe. Okay. Then we reminded ourselves how to calculate a thing like the pressure loss, pressure drop. Okay. What about in thermal considerations? You have this mean temperature, and one of the concepts we did last time was energy balance. So if you have a pipe, maybe I'd change the color a little bit, clean it up there. The wall of the pipe, and you have the entrance and some sort of exit to the pipe, and you come in here and you select a little section. You should be able to do an energy balance for flow. And so the rate at which it's flowing in and crossing at this location X, and then this is location X plus delta X, is the mean temperature at X, and then the mean temperature at X plus delta X is real important. So if I said, what is the rate at which it's flowing in on the left at location X, it would be the product of the mass flow rate, specific heat, and you have T minus a reference temperature, but often we even just drop off that reference temperature. It's going to cancel out of the equations, but it's just m dot C T. Hey, what is m dot? Mass flow rate. What's C? Specific heat. What's T? Temperature. It's like m dot times its enthalpy, if you're thinking thermo 1. All right. Likewise, you have the same equation for the mean temperature at X plus delta X, or at the outlet.
So you're not taking into consideration like environmental temperatures? It's not like convection?
And then coming across the side of the control volume, you'll have maybe a constant surface heat flux. And then if you multiply by the perimeter and then times delta X, that gives me the surface area, and that's what's added. So you have to do a complete energy balance. And so you have the flows. Most students will trip on this. They won't, well, like, where did this, m dot C T, where did that come from, and why is that for flowing in? It's a rate at which it's coming in. And then m dot C Tm for the mean temperature going out. That's a loss or flow out. And then often you have a convection. This was an easy one for the convection from the wall. If it's a specified heat flux, what happens if it's not a specified heat flux? What happens if it's just a traditional convection where you have a hot wall surface? Then what comes in from the wall would be, and I don't really know where to write it, but it'll be the H times the perimeter times delta X times the surface temperature, whatever it is, minus that mean temperature in the control volume. So either one of these, you'll see, well, oh, we're going to solve it for a constant heat flux. Oh, we're going to solve it for a constant wall temperature, or even just a specified wall temperature. And you get an equation especially for if I plot the temperature as a function of location going from 0 to L, and I have a constant surface temperature, Ts of the wall is constant, and I come in cold fluid, Tm coming in as low. What is my equation, analytic equation? It's a kind of boring exponential. And what was our equation that we derived? We derived that theta is equal to, what is that theta coming in? What's theta? Theta is that temperature difference. Then we had E, and then we had a bunch of terms, X. X being that distance. All right? I have to look at my notes to remember all the terms up there. But the terms are an H, a P, an X, and it's a minus sign on there, it's a negative, divided by mass flow rate, specific heat. All right, we already talked about what is M dot, we already talked about what is C. I think you know what H is. But what's P in that equation? Perimeter, not pressure, right, just perimeter. The T, like the TS, a little X right here. Yeah, like a time, but it's a location X. Then X goes from 0 to L. Look good? Did I put a T last time by mistake? Look for mistakes in my notes, or your notes. Okay, thank you. We spend a lot of time on laminar flow, and this is where it gets a little more tricky, so I'm trying to do an overview before I jump into it, is that you'll be trying to solve for the temperature as a function of location R for a given X down the pipe. What's that temperature profile look like? So if we kind of look at the pipe, we said, hey, what did the velocity profile look like? Well, if it's laminar flow, it's a quadratic, and we are able to solve for the analytic description of that velocity profile. All right, what about the temperature profile? Maybe I scoot down here so I don't overlap them, and I think about the temperature of the surface being higher, so I'll plot it like this, coming out, and maybe the center being colder, and you'll get a temperature profile like that inside the pipe, indicating, again, just is that it's cold in the core and hot at the surface. And just like we had no-slip velocity, we have no-slip temperature. Essentially, the fluid temperature adjacent to the wall is the same as the wall temperature. Now, to get that profile is a little more challenging than it was to get U as a function of R. That was easy. Getting T as a function of R is more challenging. Why? Because we have to go back to our governing conservation equations, our energy balance equation, and in the energy balance equation you have the flow of fluid. And so U is a function of R, and now I have a differential equation and I need to solve it. And let me just kind of jump to the conclusion. For laminar flow, we're going to be trying to calculate what's happening with the flux at the wall coming in so that we can get a relationship to get H, convection coefficient. This whole chapter, internal flow, is the hunt for H. Where's Waldo? No, not this chapter. Not Waldo we're looking for. We're looking for H. You appreciate that book, Waldo, Looking for Waldo? Yeah, it was a lot of fun. Kids loved them. Big picture book, you're looking for something. Anyway, to find H, you have to get the Nusselt number and unravel it. And so you want to get this H here. The way to get it is to find a relationship for the Nusselt number. After a lot of work, we're going to have the Nusselt number is equal to 3.66 or 4.36. It's just, after you've been in the business for a while, you use these equations a lot, and you just remember, oh, there it is. A lot of work to get that for laminar flow, fully developed, flow in a pipe, that if I have this boundary condition, where I have the temperature surface is equal to a constant. Then I have a constant Nusselt number for laminar flow. Again, the restriction, I'm trying to repeat it because it is important to remember all that. Is just a constant 3.66, and then 4.36 comes with Q double prime at the wall equal to a constant. Now, when I get to that section, I'm going to go dot, dot, dot with the four-letter word work. Believe me, it's a little bit of work to solve that energy balance ordinary differential equation where you have an analytic description of the velocity profile to get the temperature profile, to then get the gradient of the temperature at the surface, to then get an expression for the H and an expression for the Nusselt number. But then students really love it because it's like, okay, you showed me the derivation, thank you. It's impossible for a professor to ask you to repeat that derivation on an exam. It's just too much unless it's a grad class. And so then the students just kind of remember, okay, I kind of conceptually remember the pathway, and I know how to get that Nusselt number, and I know how to use it, and it turns into plug and chug. Well, if I want to add a subscript to this Nusselt number, I'll put a subscript D, because that, just like on the Reynolds number, we sometimes forget to put this subscript D on there. Sometimes we put it on there to emphasize that's our length scale for internal flow, D for diameter. Okay, we'll take a look at this section right here, turbulent flow. What do you think they're going to do? This kind of gives us a false impression about convection heat transfer, because you think, wow, so much beautiful math and all that calculus and solving differential equations. Wow, we can now continue that strategy into turbulent flow. Nope. So what you do is you look for a correlation that somebody developed based on a lot of empirical. It's empirical correlation, a lot of experimental observations. They curve fit it. And so it becomes more plug and chug. But there's one outstanding equation that I tell students. You'll see it on a final exam, probably greater than 50% chance in this class. And you're almost guaranteed to see it and need to use it on the FE exam. Yeah, and so it's the Nusselt number. Again, sometimes you add that subscript D to emphasize, oh, the Nusselt number is using that length scale, diameter for internal flow, is equal to 0.023, empirically fit determined coefficient. Reynolds number to an exponent, often that exponent is 0.8. Prandtl number to an exponent, now they go back, this correlation was developed in 1930. And they'll put an N here, and they'll say N is 0.4 for heating, 0.3 for cooling. I just say put 0.333, 1/3, and you'll be close enough for all your applications. But there you go. Okay, so this is for turbulent flow in smooth tubes, empirically based. And if you have in your mind that Moody diagram, it's not for the entire range of all Reynolds number going out to high Reynolds number. It's in that sweet spot where we just have a lot of engineering applications. You know, it's turbulent, so it's greater than 2,300, but it doesn't go up to, I think I'm trying to remember, I have it on a slide, but about 10 to the 5th. Like, what is that, 100,000? Okay. This is a simple to use equation. That's why it's used on the FE exam. That's why it's used in a final exam in a class like this. Don't you think since 1930 somebody's tried to come up with an improved equation? Yes. Don't you think that they're probably going to make it a little more complicated to fit more data and have smaller error bands? Yes. But then that's perfect for a computer code, not for an exam where you're restricted to use a hand calculator. All right. All right, now let's take a look at this section. What do you think? Convection correlations It's going to be for non-circular tubes. This always throws people off. Sometimes they'll say non-circular pipe or whatever. You know, what are they talking about? Something like this, right? A duct, rectangular. Or you could have something crazy. You could have the flow in the annulus where you have an inner diameter and an outer diameter, and the flow is in this annulus region. We'll go back to your fluid mechanics background. What would you do there? You want to calculate pressure drop, flow in a duct, it's not round. You want to calculate pressure drop, flow in the annulus, how would you do it? You would use D subscript H. What's D subscript H? From fluid mechanics, hydraulic diameter. And then once you have an estimate, kind of an equivalent diameter for the system, then you can go and use your traditional correlations. Now, they do a better job if you have laminar flow. They have worked out a lot of analytic solutions, and we'll show in a table. But for turbulent flow, it's kind of like, okay, get the hydraulic diameter and then go use the round tube correlations. Go use that Ditas-Volter, that 1930s version of a correlation. All right. What about heat transfer enhancements? Don't you think engineers have tried to enhance heat transfer within tubes? Oh, sure. There's a lot of enhancement techniques, and they're in practice, a lot of them. But in the interest of time, we have to just skip it. What about small channels, micro channels? Hot topic, or it had been for a number of years. Heat transfer in really small passageways, but in the interest of time, you know, it's just a subset. And then convection mass transfer, we've been skipping that. But that's real important on a hot day. They say yesterday it's hot and humid and you're trying to reject heat. What does your body start to do? What does your shirt fill up with outside? Sweat. And so it's really important, convection mass transfer. Evaporative cooling is very important to a lot of applications. Well, I spent a little more time on this slide because I know that once I jump into the weeds, sometimes we get lost. Hopefully you have a good roadmap. You ready to go? All right, let's go. This is what we did last time, did we not? And I think you said I put a T there, probably by default, because this equation looks a whole lot like lumped capacitance, that exponential solution on lumped capacitance. But what did we do for this temperature difference as a function of location x going down the pipe? We did an energy balance on a small section, and then had our differential equation, initial condition, solve for it. All right, now, this is where I left off last time. We did some calculations. I said, what happens if the temperature difference on the inside, like the theta 1 is maybe 50 degrees C, and theta 2 is 30 degrees C, and you want to use a simple approximate equation that says that the Q, in the red box right here, Q is equal to HA times an appropriate temperature difference between the hot surface and the cooler fluid flowing in the tube, and it's the log mean temperature difference. And then we said this is it. It's I wrote it last time as delta T on one side minus delta T on the other side divided by the natural log of delta T on the first side divided by the delta T on the second side, or end. But that's the same equation. Instead of thetas, I put delta T's, but that's what theta is. Okay. How did this equation come about? Well, I also can guarantee that 50 to 70 to 90% chance that you're going to need to do a delta T log mean calculation on the final exam in this class. Likewise, there's probably a super high probability of using it on the FE exam that everybody should be thinking about taking their last semester at UTSA, right? How many people are planning on taking the FE exam? Smart, very smart. All right, good. All right, here's the derivation, and you already have the exponential for the temperature distribution. It's really just a packaging. And so you know that you have this equation for the rate equation. It's Newton's law of cooling. What is this equation coming from right here? Somebody says, I think this is Fourier's law, this equation right here. No, that's not Fourier's law. I think that's Stefan Boltzmann's law. No, that's not Stefan Boltzmann's law. What is this equation? How would you describe? Somebody says Q is equal to m dot C times the change in the mean temperature between the inlet and the exit. Oh, it just fell out of the sky. Look, I don't know where these equations come from, Professor. They just are in the book. What is this equation? There's a lot of equations that you use. Like if somebody says, what rho GH? You say, I've seen that. I've used it. What's it do? It's like hydrostatic pressure, right? Rho GH. It's, all right. Now you see this something like m dot C times the change in the fluid temperature, the mean temperature of the fluid. What is that? I feel like a dentist trying to pull teeth right now. Come on now, help me a little. What is that? Take a wild guess.
Common sense.
What?
Common sense.
It's common sense, okay, but where did it come from? How did you say, I agree with it? That's what you're saying. I agree with it. It looks reasonable, but why? What did it come? What's it a statement of? Somebody says, this equation. Yeah, Newton's second law. And there's a lot of other. I threw out. I said, no, this is not Stefan Boltzmann. No, this is not Fourier series. This is not separate, integrate. This is not, I don't know. There's a lot of stuff that you know, Leibniz rule. No, it's not Leibniz rule. No, it's not L'Hopital's rule. No, it's not Kramer's rule. I guess I'm on rules right now. What is this? It's just an energy statement. So it's kind of like a global global control volume, and I have what comes across from the side, Q. In thermo, we used Q dot, and often the Q is capital, but this textbook uses lowercase q without the dot for the rate of heat transfer. And if it's coming in the side of a large control volume where I have fluid flow coming in on the in and going out on the out, something's going to happen. It's going to heat it up. It's changing its enthalpy, and the enthalpy is we're approximated as a C times T, specific heat times temperature. So we have m dot, change in enthalpy. There you go. It's energy balance for the whole system. So you take that energy balance for the whole system, you have a temperature distribution, you have a form of the equation that you want, and then you force this and this to package up to make the equation like you want, and then you get the conclusion is this is the appropriate way to express a temperature difference. It's called the log mean temperature difference. If the pipe was small, short and stubby, and there wasn't a great change in temperature, maybe it came in at 50, went out at 30, then you could just use another average, arithmetic average, instead of a log mean average. But if there is this shape where the profile really does experience some curvature in it, the mean temperature is changing like that as a function of location going down the tube, then you better use the log mean temperature difference or you could get some error.
I forgot what part of the pipe you were looking into. Was it before it fully developed or is it after?
Okay, the log mean temperature difference is, this H is going to be assumed to be a constant. So if you have a significant entrance region, then you need to get the average over that length, where the entrance region H is going to be higher. A little bit of work. All right, now you're ready to get into something more difficult. That was too easy. You were being bored. You were falling asleep. You weren't even answering my questions because you were so bored. It was so easy. Now let's get into something a little more challenging to wake you up. So we're saying, as I tried to allude to at the overview, you want to get a a differential equation so that you can solve for the temperature as a function of R, so that you can get an equation eventually for the Reynolds number. All right. This equation right here, it's kind of like the starting point. What is this equation? Where did it come from? Do you recognize any parts of it? Like what's over here on this side, on the right-hand side? What does that look like? It looks like a Laplacian. It looks like that spread of heat due to diffusion. It's a diffusion transfer of heat. It's like Fourier's law is in there. If I put in a K right in here, thermal conductivity, that's going to come from that alpha. Remember, alpha is K divided by rho C, so you kind of take the K. That's where that alpha came from. They took the K out from inside. Okay, then I look over here. Well, this alpha, I put that rho C back over here, rho C. What's that look like? On the left-hand side, advective transport of energy. So if I'm doing this control volume, I shrink it down to an itty-bitty small point, then I get a differential equation. This is really a heat equation. It's an energy balance statement on a point, not a volume. You have the advection, diffusion. They're balanced. Advection is in, for my pipe flow, the advection is in the X direction. What about the direction for the heat diffusion? What's in the R? It's in the R direction. Remember, our temperature profile typically is hot, cold, then back on the wall. So it's the diffusion would be in that direction of heat from the hot wall surface to the cold interior. All right. Now that you understand that equation, what are we doing right here? We're saying, hey, we already solved for U. What's U again? Our velocity. But it's not a constant. Our velocity profile, does it look familiar? 2 times UM. Isn't the mean temperature multiplied by 2 equal to the maximum temperature? Yeah. So we have the maximum temperature times 1 minus R over R squared, that quadratic profile. All right, you have a good differential equation. You look at it. Is it first order, second order, third order, fourth order? You know, it's only T. You're only trying to find T as a function of R. And I look at the highest derivative. It's only a second derivative. It's second order. It's an ODE. All I need is 2 other conditions. Because I'm looking at R, it's not time. I don't call them 2 initial conditions. I look at 2 boundary conditions. What's this one? It's a boundary condition at R equal to 0 at the core right in the middle, and it's that slope is equal to 0. That's a common one. Okay, and then what's the other boundary condition? We have to understand our differential equation before we solve it. So how would you describe this to a friend or a cousin or somebody who's a high school student and they want to become an engineering major? You know, this is the type of thing that we master. These are the type of things. What is this? It's Fourier's law at the surface. And so what's being pushed into the fluid has to go through that first stationary layer of no-slip fluid right at the wall. And so what is the K here? Is the K the thermal conductivity of the solid wall? Or is the K of the fluid? Answer A or answer B? And let's take a look. So we'll just show the results. And well, it's not of the solid wall, it's the thermal conductivity of the fluid. It's just into the fluid. We're really trying to solve for the temperature as a function of R. In the wall or only in the fluid? Only in the fluid. Only in the fluid. So this is no. It's the fluid thermal conductivity. This is Fourier's law. Maybe the mathematicians would put that R is equal to R minus. Does that make sense? You ever seen that? The little mathematician writes it like that. It says it's like or another way to put it, minus an epsilon, a small amount. It's just a little bit below cap R. Okay. Anyway, but that's what I have to summarize. You do it for two cases. You do it for the first case where the flux is constant surface heat flux. You remind yourself that the mean temperature is going to go up linearly as you flow down the tube. The surface temperature is going to go up linearly, and there's a constant theta temperature difference everywhere because it's a constant heat flux. We talked about that before. So you have now a long differential equation. You want to start applying techniques of separating and integrating. I think I tried to write the whole equation right here with that expression of the velocity as a function of r, that quadratic. You separate, integrate. Maybe I'm shortchanging you, but underestimating your mathematical capabilities. But yes, you can do this. It is tedious. Look at what do you get here? R to the fourth power. It's not r squared. So that temperature profile is not a quadratic. It's a little more complicated mathematically than r to the 2 power, r to the 4 power. Did I just say ... right in here? But now that I have the temperature as a function of location r, it does change as we go down x, doesn't it? The mean temperature is changing. It's fully developed, so the profile just kind of grows, but it's not changing shape. We recall the definition of the mean temperature. Does that look familiar? All right. We then go back and say, what was our equation for the mean temperature, how it changes with the function of x compared to the constant or the surface temperature as a function of x? You have to substitute the t in here, the u in here. You could do the integration and you get the nice packaged equation right there using this temperature profile. From our global energy balance, the slope here is related to Q double prime P divided by rho C U sub M A. What is Q double prime? H delta T. So I have this solution for the temperature gradient. I put it right into this side on the energy balance, and I solve for the H. So I'm able to cancel these terms, and I'm trying to keep it on one slide, rearrange or repackage, and you're looking to package up and see what that Nusselt number is. The Nusselt is a HD over K, and you find that it's 48 over 11. Somebody that did this a long time ago. A lot of work, but you round that off, 4.36. People don't remember 48 over 11, they remember 4.36. That was for the easier case. What's the second case? Instead of having Q double prime a constant, what's constant? Oh, wall temperature. And so here's the second case. Same differential equation, same velocity. What I need to do is I have the same boundary conditions, but my the temperature is a function of x, like this, and dt m dx is not a constant. So I'm really looking for this function of r times dt of the change in the mean temperature with respect to x. So this is a little, I wouldn't call it a trick, but insight that an analyst has in order to solve the problem. Setting it up, you have this added function and then dt dx. You come in, you separate, integrate, you remind yourself of the mean temperature. I'd use a couple 3 dots here and a couple 3 dots there, because you can get it, and the book has that description here. And you equate the global energy conservation statement with your solution to the temperature profile, and you look to package up a Nusselt number, and it comes in 3.66. If it was a grad class, maybe we'd spend the whole day on it. But in the interest of time, we press forward. So let's summarize. If you have laminar flow in a round tube, if you have constant wall heat flux, 4.36 for the Nusselt number, and if it's a constant wall surface temperature, 3.66. Now, smooth tube only, less than Reynolds number critical of 2300, and the entrance region, it needs to be beyond that entrance region. And this was our equation for the thermally fully developed entrance region. All right. Solve a problem. Fluid at a given flow rate is heated from 25 to 75 degrees C. So we know the inlet temperature and we know the exit temperature. They're really giving us the mean inlet and the mean exit temperature. The thin walled diameter tube, which is so long, 10 meters long. A uniform heat flux is used by, maintained by electric heater wrapped around the tube. For fluid properties, sometimes I do this to make it easier. Don't chase the table. If you've gone into the table and gotten fluid properties a few times, it's just work. But here's use this value of rho, specific heat, mu, thermal conductivity, and Prandtl number. Okay, first of all, what is that heat flux that's required? How do they calculate the required heat flux for this problem? Large control volume, energy balance. So it's like the whole pipe, so something like that. And when you have the whole pipe and you know the T inlet and the T exit, the T inlet was 25 degrees C and the exit 75 degrees C, basically energy balance says that this heat flux times the perimeter times the length tells me the total rate heat added, and that has to match the mass flow rate, specific heat, and the change in temperature. It came out hotter than it came in. And there's only one unknown in this equation, and that's Q double prime. Again, the hard part is, where did that equation come from? Hey, it makes sense to me. Well, you got to do better than it just makes sense to me. Where did it come from? It's an energy balance for the entire system. Okay. That's how you solve for part A. What about part B? A little easier, isn't it? Somebody says, calculate the Reynolds number. How do you do that? Well, you have to remember the equation. Rho, U, or if you want to add a subscript M on it, the mean velocity, D divided by mu. We have our fluid property, rho given, mu given, so that's two of them down. Do we have our diameter given? Here's our diameter. So that's done. I have to get the mean speed. Do I have the mean speed? They even do that right here. You know what? If I back up here, I wasn't given a mass flow rate, was I? I had to calculate m dot. Isn't that rho times u mean times the cross-sectional area? What's my cross-sectional area? Pi d squared over 4. Where this is my d right here. All right, so I backed up a little bit, talked a little bit more about part A. Now let's jump to part C, or question C. What is the distance in the pipe to be fully developed thermally? So we want to calculate to be fully developed. Not hydrodynamically, don't put an H there, put a T there, to be developed thermally. What was our equation? 1/20th of we have a diameter, we have a Reynolds number, and we have a Prandtl number, right? Okay, that's for laminar flow. Do we have laminar flow when the Reynolds number is 1143? So it's a laminar flow. So I kind of jumped to this equation. What happens if it would have been 11,430 for the Reynolds number? Can I use this equation? No. What equation would I use? 10 diameters. 10 diameters. Okay, but we have laminar flow, so we use this equation. And the 1/20th, the diameter known, the Reynolds number calculated, Prandtl number is given right here, 10. Okay, let me do this. What is the equation to be fully developed hydrodynamically? 0.05 d times Reynolds number for laminar flow. For this problem, is the distance to be fully developed thermally compared to the distance to be fully developed hydrodynamically. Is it greater? Answer A. Equal? Answer B. Or less? Answer C. How do those two distances compare? The thermal entrance length versus the hydrodynamic entrance length. So we'll stop it. Remind ourselves that this part of the equation and this part of the equation, they're the same for both of them. And so it's really the scaling. The hydrodynamic is the thermal is the hydrodynamic times the Prandtl number. And for this case, the Prandtl number is 10. So the thermal entrance region is longer. All right, so the correct answer is A. Ooh, that's pretty good. All right, so it computes to be about 7.3 meters. Part D. What is the convection coefficient at the exit of the tube? Well, again, the emphasis on the exit. The tube length is how long? 10 meters long. It's going to be fully developed after 7.3 meters. So what do you think? How am I going to calculate the convection coefficient at the exit of the tube? So this is one of those things that you just have to say, oh, it's laminar flow. At that point, it's going to be fully developed in the pipe. I have to look at the type of boundary condition that I have. Do I have a uniform heat flux? I do. And so the Nusselt number is a constant. It's 4.36. And then the definition of the Nusselt number is H d divided by K. So I just unravel it. H is equal to 4.36 times K divided by D. And then you put in your H and your D and you calculate 275. Now, what is the surface temperature of the tube at the tube exit? So the wall temperature at that exit. How am I going to solve for that? Big hint, use that the mean temperature of the fluid at the exit is 75 degrees. So somebody volunteer and describe how you're going to solve for the surface temperature of the tube wall at the exit. I'm sorry? Do a local Newton's law of cooling. So down here, just like right here, just like right here, just like right here, you're driving heat at a certain rate across the surface area into the fluid, into the fluid in the pipe. And so Q double prime at the exit is equal to the H at the exit. That's why part D was required or asked for, times the temperature of the surface at the exit minus the mean temperature of the fluid at the exit. because this is constant, I don't need to emphasize that it's an exit. It's a uniform heat flux. So the temperature of the surface at the exit is the temperature of the mean bulk or fluid temperature at the exit plus Q double prime divided by H. Make sense how to get 117? Somebody asked, can you sketch the temperature profiles starting as a function of x going from 0 to the exit L? And we said that it was the fluid came in at 25 and it went out at 75, right? So what does the fluid mean, or the bulk fluid temperature do, the mean temperature do? Does it do something like this for this problem? Or does it something like this for this problem? Or something like this for this problem? You know, it's answer A, B, or C. What is the profile of Tm, the mean temperature of the fluid, through the pipe? And we go ahead and show the results. Well, why is B the correct answer? What? I'm sorry? Constant heat flux, exactly. Basically, you're pumping in the same amount for every inch or every foot or every centimeter of length. Hence, it's going up by the same amount every inch or foot or centimeter of length. It's constant heat flux. Okay, now that we know what Tm is doing, that's our mean temperature going straight. What does our wall temperature do? And let me just say that I'm going to come out here and I'm going to say after a distance, this L is 10 meters, right? After about 7 meters up, I can't, what is the number here? After 7.3 meters, it's fully developed. Okay, so at 7.3 meters, the theta is constant. That makes sense? So I know that the temperature of the wall or the surface is higher by a fixed amount after it's fully developed. And I don't think we calculated the physical temperature of 117. So this was 117. This was 75, that's 25 and 17, what is that, 30, 42? So this theta here is 42. Did I do the math correct? 42 degree temperature difference? So that's the same. Okay. But what about down below, before it becomes fully developed? Do I have a profile that may be, is it small and then go to 42? Or does it stay at 42 everywhere? Or is it higher than 42 and then goes down to 42? I'm looking for the temperature of the wall in the region where it's developing. So answer A, or answer B, or answer C. This is a little harder question. Well, in the entrance region, what do we know about that boundary layer? It's steeper, isn't it? It's the middle of the pipe hasn't felt the effect of the presence of the wall yet. And so you have a higher wall shear stress, and you're going to have a higher convection coefficient. So H, if I plotted H as a function of distance, out in here it's a constant H. What was that H? Well, we calculated that H to be 275, didn't we? Watts per meter squared Kelvin. What does the H do? Does the H do that? Yeah, it's higher at the entrance region. It's got greater gradients for both drag as well as for the convection. And so H is higher. We talked about that last time. So because it's higher, then we look at the Q double prime is equal to the H times the delta T. This is greater, hence this doesn't have to be as large, the temperature difference. Hence the right answer is A. The theta is smaller, the temperature difference is smaller. Until it's fully developed, and then the temperature difference stays 42 degrees. For this problem, let's grade it. It's pretty good. 70%. So in the textbook, if you do not have fully developed and you really need to solve the problem, use a figure. The figure's a little bit of interpretation. I don't know if you need to use it for a homework problem or not, but out here, it's like you have the entrance region, and you can see that you have a higher Nusselt number. Depends on if it's constant surface heat flux or constant surface temperature. Depends if it's thermally the entrance region or combined. What do you mean by combined entrance length? What do you think could also be developing? The velocity profile. You could have an application where the pipe goes like this, and then this is where you start to have this may be well insulated, and this is maybe where it's heated. So it could be hydrodynamically fully developed, and then all of a sudden, boom, oh, now I'm going to start developing thermally. There's no end to these problems, is there? What did they do between here and here? The average. A lot of times we're not interested in what the local H is. Sometimes we are, but a lot of times we're interested in what's the average from the beginning to the end. Okay. Notice that what do they have here? What is this Reynolds number equal to 0.7? What are they talking about? It's a little red flag. It says to the reader, oh, well, who has a Reynolds number of 0.7? Air. Air. Not water. Air. All right. But if they come out here and they have, oh, the Reynolds number is 2 or the Reynolds number is 5, well, now you're in the range of water. Water has a Reynolds number 2, 5, 7, sometimes for cold water 10 or so. All right. Okay, what about, we don't have a circular tube, we have a non-circular tube, but we still have laminar flow. What do? Well, people have worked hard and they've tabulated a lot of results. So here's a reminder for the friction factor. This is F times the Reynolds number. It's a little bit offset, but that's equal to 64 for the round tube. Does that look reasonable? Remember, F is equal to 64 divided by the Reynolds number. That's the equation often put on the Moody diagram. So this is familiar territory. And then look, oh, 4.36 if you have constant wall temperature, constant heat flux, or the constant wall temperature 3.66. That's all familiar territory. But you come over here, square, different rectangles or shapes at different aspect ratios, and somebody's worked out the Nusselt number for constant wall heat flux as well as constant surface temperature as well as the friction factor. All right. I wish more engineering applications had laminar flow. It'd be kind of nice. It's like, oh, this is great. We have analytic solutions. But most engineering applications don't. Okay, come back here. And what do we have right here? I know that I wrote the Reynolds number is a function of diameter, but they put another subscript on the subscript. What? Can you kind of see it right there? What did they put? A subscript H on the D. So, clicker question, this is be easy. What is this D with the subscript H? Is it the heavy diameter, the head diameter, the high diameter, the hydraulic diameter, or the hilarious diameter? Okay, why do I not have 100%? Is somebody texting in or playing with us from their couch or bedroom this morning? Okay, all right. It's hydraulic diameter. That was the easy one. So what is the definition of the hydraulic diameter? Where A subscript C is the cross-sectional area and P is known as the wetted perimeter. All right, do this. If somebody says A sub C is a cross-sectional area, and I said, give me the typical expected SI units for that term, AC. Somebody said, newtons. No, no. Joule. No, not joule either. It's an area. What is it? Meter squared. All right. Somebody says wetted perimeter. Give me the anticipated SI units for the wetted perimeter. Meter or meter squared or meter cubed? Meter, right? So if we just look and we say hydraulic diameter, what do you anticipate? Anticipate the SI units for the hydraulic diameter to be? Meters or inverse meter? Which one? Meter. So if I look at these, which ones can I throw out? Because P would be, look at A. It would be meter divided by meter squared. Are the SI units going to work on that? Throw it away. All right. How about P over, no. So A or B is out. All right. C or D. Now the other thing is if I say, if I have a round circular tube, and I say calculate the hydraulic diameter of the round circular tube, do you think it should equal the physical diameter of the tube, or should it be 2 times or 4 times or 1/4 of the physical diameter of the tube? I mean, what makes more sense to you? Should it be 1/4 of the diameter, or 1/2 of the diameter, or equal to the diameter, or 2 times the diameter, or 4 times the diameter? Answer A, B, C, D, or E. If I say, use the same formula to calculate the hydraulic diameter of a round tube, what should it be in terms of diameter of the tube? We're done. Let's stop. I was going to hope that most of us would nail this one. Wouldn't it be confusing if the hydraulic diameter didn't equal to the physical diameter if you applied the equation to a round tube? Anyway, it would be more confusing to the world. So if the hydraulic diameter equals the physical diameter for a round tube, what is the equation for the cross-sectional area of a round tube? Pi d squared over 4. And then what's the perimeter? Pi d. So if we say that if I just put AC over P, then it would be pi d squared over 4 divided by pi d. It's d over 4. That don't make any sense. So what's the best answer? Isn't it? Yep, 4AC over P. Sometimes people are like, where did that 4 come from? Why is it there? Well, that's why. I tried to explain it. Well, guess what? We leave the realm of laminar flow and we must go to turbulent flow. When you go to turbulent flow, I really think you should have in your mind the Moody diagram. And in the Moody diagram, you should also say a lot of engineering applications are in this region of pipe flow, and a lot of engineering applications are sort of smooth pipe. So guess what? A lot of convection correlations are based on a limited range of Reynolds number in the turbulent region and are restricted to smooth pipe. That's the name of the game. So one of the great equations we came out with at the end of chapter 6 was the modified Reynolds analogy. It's basically relating C sub F divided by 2. If I multiply that by the Reynolds number, the Prandtl number to the 1/3, I anticipate the Nusselt number. So we're interested in using this equation, but what is the difference between C sub F and F? The fanning, or the fanning friction factor and the Darcy friction factor. Factor of 4. So sometimes I'll write the Darcy friction factor divided by 8 times the Reynolds number times the Prandtl to the 3rd is equal to some Nusselt number. You know what? You can stop right there. You can use the Moody diagram, and you can do a lot of calculations of getting the Nusselt number, then getting H. Remember, this whole chapter is find Nusselt, then find H. Often that's the recipe. Using this equation. Get there. I mean, worst comes to worst. You come out there and say, well, what's my Reynolds number? What's my friction factor? Oh, I come up here, you know, there, I pick off a friction factor and I plug it in. It'll get you in the ballpark. It's actually pretty good. And a lot of our correlations are based on that. What you can do is you can come out and say, hey, the Blasius correlation was for turbulent flow in a smooth pipe when the Reynolds number is less than 10 to the 5th. So it's only in this region right in here. And you can take that F, shove it right there, and you can get now an expression. You can skip the Moody diagram, but it's restricted to smooth in this range of Reynolds number. And in that, you'll get 0.316 divided by 8. You'll get Reynolds not to the 1 power, but you'll get it to the what power? 0.75 power. You'll get Prandtl to the 1/3. Do me a favor. Do you have a calculator? I'll do it too. 0.316 divide by 8. What is that number? 0.0395 Reynolds to the 0.75 Prandtl to the 1/3. That's your Nusselt number. That's a pretty good correlation. But this is where some students may get confused, because one person does this, one person does that, they publish a paper, they publish another paper, and before you know it, you have so many correlations, your head is spinning, and you're saying, which one's better, which one's better? Well, Thetis Volter is simple to use. It's been out there for a long time. You can see the structure. Instead of the Reynolds number to the 0.75, what's 4/5? 0.8. Instead of a Prandtl number to a constant 1/3, 0.3333, they say, oh, if it's being heated, use 0.4. If it's being cooled, use 0.3. If somebody says, I don't know if it's heated or cooled, what do I use? I don't know, 0.35, close enough to 0.333 anyway. You put that, the true Thetis Volter says you need to know if it's being heated or cooled and use 0.3 or 0.4. Okay. And then 0.023. What did we just have on the previous slide? 0.04. So, all right. So you can see this one is out. Again, this one, if it's applicable, these are the range of the Prandtl numbers, 0.6 to 160. That covers air and that covers water. So you're good for a lot of fluids. All right. Reynolds number greater than 10,000. So it's really further out on the Moody diagram. Here's 10,000 right there. It's pushing out this region. They don't really put a restriction on there. I'd have to go back and take a look at the max Reynolds number. I don't remember max Reynolds number. I don't think this book computes a max Reynolds number. And what's this? L/D greater than 10, fully developed turbulent flow. And they say to evaluate the fluid properties at the mean temperature of the fluid. But the mean temperature of the fluid is changing down the pipe. Well, if you want an average H, get an average mean temperature to get the average fluid properties to then do the calculation. Here's another one, Sider-Tate. I think both this one and this one are available during your exam, the FE exam. In the FE exam, there's used to be a paper book that they would give each person taking the test, and then you would leaf through it on the paper exam. But now it's all computer-based. So the PDF file of the handbook that's available. So you'll be sitting at a computer and you'll be able to then access the PDF while you take your computer-based FE exam. Okay, so, but it's still, this equation, the Sider-Tate's available. This one is not in that handbook. It's a little more complicated, and come on. These equations on those, they're just testing your basic knowledge. Now, if you take a look, that coefficient's really close. Reynolds number to the same exponent. Prandtl number to the third. I like that even better personally. And what do they have here? This is common adjustment for the effect of the surface temperature, because in the true Dietz-Boelter, the surface temperature is not really used. But the Sider-Tate has the mu over mu sub s. What do you think that subscript s is for? You evaluate that mu sub s at the surface temperature. So it's the fluid viscosity evaluated at the surface temperature. And it's not that strong of a exponent, 0.14, but there it is. That's based on experimental data. Okay, what about this? Another one they publish, and I know there's plenty of them out there. What do? They have the friction factor, they have the Reynolds number, the Prandtl number. They have the range of the Reynolds number, fully developed, evaluate the properties at T sub m, just like the other correlations. And all of these are for smooth tubes. Somebody says, what happens if you have a rough tube? Two things you can do. You can use this equation and use the F. Even though it was not developed with smooth tube data, you can still extend it a little bit. And that's actually what the book says to do in some cases. Or you can just forget about it and go back to this equation right here. That'll work too. Just go back to the modified Reynolds analogy. Get the friction factor off the Moody diagram and go that way. I think in one problem they say to use this correlation to avoid the ambiguity. Just use this correlation for a rough tube. All right, I like to bring this book when I teach this class. Can you tell from the cover of this book? Does it look like it was recently printed? If you open it up, maybe even from the distance you get that musty smell. Maybe you can smell it from your seat. Yeah, I can smell it. This is an older book. This is a book published in 1954. I don't know if I have the first edition of this book or not. I didn't look. It says 1954, third edition, okay? So Heat Transmission, the title of the book, it's by McAdams. It's a well-cited textbook. It's often cited. You'll find it cited in lots of heat transfer textbooks today. And on a particular page that they talk about the Sider-Tate and Dietz-Boelter correlations, on page 219, it's very interesting because up here they have the description of the same equation, and down here is a little footnote, and they say maximum deviations were about 43 to minus 33%. What do you think about those percentages? You're going to go on a job interview. They're going to say, oh, we're going to hire you and we're going to pay you, I don't know, somewhere, let's throw out a number, $70,000 a year. But we don't know yet. It could be plus 43% of that or minus 33% of that. What do you think? There's a huge uncertainty, error band. That's the nature of convection correlations. Had one professor, he said he didn't believe any plots of data in curve fitting until he could use his 2-thumb rule. Put one thumb above the curve and one thumb below the curve. And if they didn't cover all the data and some of the data was still sprinkled outside, then he kind of believed it. If it was too tight, he would say that the people fudged the data. So 2-thumb rule. Anyway, that's the nature of convection. So in there they have this line. It is clear that equations of the forms of the products of the powers of the 3-dimensionless groups. They had the Nusselt, they had the Reynolds, they had the Reynolds number. And they're just powers and products of, with an exponent, each with an exponent, exponent 1, exponent 4/5, exponent 1/3, 0.4, 0.3, are, how do you like that word? But everybody cites this book as the source for the Dietz-Bolter recommended correlation, which in this book says it's an inadequate. Don't think that you have all this precision. These empirical correlations, there are a lot of people publishing different ones. They've improved. You're getting in a textbook, introductory heat transfer textbook, some old ones, and but they're still used today. They're just used with the knowledge that the engineer has to account for a lot of uncertainty in the design. Have a good control system on your heat transfer. All right. All right, turbulent flow, but you have non-circular. What do? Use that hydraulic diameter, d sub h. And then once you have the value of the hydraulic diameter, go and use the correlations that are for circular. A little different than laminar, because in the laminar, some people worked out what the coefficients would be based on the boundary condition. Is Q double prime constant or TS constant? All right. Internal flow, how do they augment or increase the heat transfer? Sometimes in the inside of a tube, they'll put a coil, kind of like that. What's that coil doing? As the flow goes down, it's impeding the flow a little bit. You're going to have a higher pressure drop, but what's it doing? It's tripping it up and improving the heat transfer. Sometimes they'll have little protrusions. What does this longitudinal, here's that word I was going to cover up, but what does it look like? They put little internal fins on the inside. Now this is going to be an expensive tube to make, and I haven't seen many of these, but there you go, because you're going to have to manufacture that. This one's very common. They put a twisted tape inside. Twisted tape. It's cheap. You just insert it, and now instead of the flow kind of just blowing through, it's being forced to twist and rub. Hopefully, if you like that word rub, maybe I shouldn't use that word rub, but promote the heat transfer from the wall. Or then they have a helical rib, like 2. Okay, so anyway, it would be more empirical correlations. You can take a look at that section. I don't have any exam problems using this, and I don't have any knowledge that they're ever tested on the FE exam. Let's solve a problem. So we have air, 12 degrees, enters a 2-meter long, smooth, but it's a rectangular duct with a cross-sectional of 75 millimeter by 150 millimeter. So there's your duct. The duct is maintained at a constant surface temperature, not a constant heat flux, constant surface temperature. The air mass flow rate is given for the air. For air at 350 K, 1 ATM, here are some properties out of the table. Okay, and you can go look at the table and verify that those are properties for air at 350 K and 1 ATM. What is the hydraulic diameter of the duct? How do you calculate part A? 4 A sub C divided by P. So 4 cross-sectional area divided by perimeter. So 4 cross-sectional area is 0.075 meter times 0.150 meter divided by the perimeter is 2 of 0.075 plus 2 of 0.150, and the answer will be in meters, and there you go. I think that's doable. What is the Reynolds number? Well, are you going to base it on the hydraulic diameter? I don't like that when you have a subscript on a subscript, but there it is. It makes that H really small, doesn't it? Okay, so you have rho, which is known, the mean velocity, but they don't give us a mean velocity, they give us a mass flow rate. So we're going to have to calculate that in a minute. The d sub h we just calculated divided by mu. How do you calculate u sub m? Well, they give us a mass flow rate. So you divide that by the mass density and the cross-sectional area, and then you have the mean velocity. Or if you don't like that equation, go m dot's equal to rho a u. That's all we did. Calculate the mean velocity that way. All right, comes in at 42,735. Red light, bling, bling, bling. What's it say to you? Turbulent flow. Now they say, what's the Nusselt number? How are you going to calculate the Nusselt number? Well, use a correlation, one of those correlations. You want to use Sider-Tate, Dietz-Bolter, what is it, Janaleski? I butchered his name, I'm sure. I would use Dietz-Bolter is easiest. 0.023, Reynolds to the 0.8. Prandtl, is the fluid being heated or cooled? I think it's being heated, then you put a 0.4 on the Prandtl number. We should make sure the Reynolds number is not outrageous. It looks okay. So we get that the 0.023, Reynolds 42,735 to the 0.8. Prandtl number is right there, 0.7 to the 0.4. Who has a calculator? Can you run it just to see? Does it look reasonable? Yeah, 101. So we verified it. Just make sure that you don't mess up simple calculations on exams. Okay. Now, how do I get that convection coefficient H? Well, the Nusselt number is defined as HD, that's our length scale for the Nusselt number, divided by K. So H is equal to the Nusselt times the thermal conductivity divided by the diameter. We had 101. We had the thermal conductivity, 0.030. Hydraulic diameter, 0.1. I didn't put my units, but it's watts, meters squared, Kelvin. And you should get around 30. Then what is the outlet air temperature of 39 degrees? How do we calculate this? 39.2 degrees C. How do we do that? Because it's a constant surface temperature, we probably want to think about putting our temperature as a function of x, going from 0 to L, and there's our surface. We're coming in at this temperature. It could be an exponential that goes like that. It could be an exponential that goes like that. It could be an exponential that goes like that. There's a whole range of conditions. But we probably want to use that exponential equation for the theta that we derived. What was that equation? So the theta at x equal to L is equal to the theta initial coming in E to the minus, then what do we have here? HPL. I'm really botching that, aren't I? Get rid of this 0.1, 0.1. Okay. HPL divided by M dot C. So our theta coming in is 127 minus 12. Then E to the minus dot, 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 all that. And you get a theta on the exit at L. And theta on the exit at L, I should have said what that is. That's TS minus TM at L, the exiting mean temperature of the fluid. And so the final temperature, TS minus theta at the exit. And it comes in at 39. So if we look at it, try and put it to scale, it comes in at 12. Here's 127, and it goes out at 39. It's not being heated that much. I mean, if it came out 125 or 120, yeah, that's the shape would be different, but it's like this. Make sense? All right. All right. Somebody says you used the Dietz-Boelter equation for that last problem, and we guessed that the temperature of the fluid was 350 throughout the tube. If I take a look at it, it came in at 12. The mean temperature of the fluid exit was 39. Is that what I just calculated? I have to go back to look. I forgot already. Yeah, 39. Okay, so what is my average mean temperature of the fluid? 12 and 39. You divide by 2. What does that come out to be? I don't know. Comes out to be 25 and a half, 25.5 degrees C. I want that in Kelvin. Add 273. And it comes in at 298 Kelvin. That's kind of an average mean temperature of the fluid. My initial property evaluations were at 350 Kelvin. What do you think? If I really want to improve my answer, this is a little ridiculous because Dietz-Boelter is good to plus or minus at minimum 25%, right? What do you think? What do you think? Well, you go back and evaluate all your properties at 300 and you redo. Well, how did the density change? Well, okay, that's a significant change. How about the specific heat? Not really. How about the viscosity? Well, yeah, there's some change there. How about the thermal conductivity? A little bit. How about the Reynolds number? Not really. But if you rerun all of these calculations again, because I think it's a good exercise, because sometimes, you know, in Wiley Plus or you're grading something or you're doing some calculations, you don't, if you're not fairly close on your fluid properties, your answers are going to be different. So, okay, does it change the hydraulic diameter if I change this from 350 to 300 and reevaluate the properties? No, that stays the same, 0.1. How about the Reynolds number? Does it change the Reynolds number? Well, it changes from 42,735 to 48,152. So, how about then the Nusselt number? It changes to 112. All right, what about the convection coefficient? It changes to 29.4. And what about the outlet air temperature? It changes to 38.5. So if you're doing something in Wiley Plus and you really didn't know what fluid temperature to use to evaluate your properties, Now you know both the inlet and the outlet mean temperature of the fluid. You didn't get the right answer, and it's probably off by 2% or more. Then try to reevaluate your fluid properties and repeat. Because I'm not certain, I mean, Wiley Plus is just a tool. There's some bad things about it. But is this plus or minus 2% difference or not, in your opinion? Well, if you converted to Kelvin, it would easily be within the 2%. But I don't know how they do it with the degree C, right? So, to me, those temperatures for convection calculations are the same. So now, what do they change right here? You're not in a smooth duct anymore. You're in a galvanized steel duct with a roughness of 0.15 millimeter. How are we going to solve that problem? Because we used Adidas bolter for a smooth. Well, you could use the Adidas bolter and ignore the roughness. You'll be close. But if you really wanted to do a better job, what would you do? You would use the roughness. Now, there's two approaches to it. You can use the third correlation that we've shown that's in the textbook. It does have a friction factor. That correlation is developed for smooth tubes but can be extrapolated to rough tubes. And that's what I did in this calculation here. It's the GNIELINSKI. But there you go. It's just more work, isn't it? If you remember that equation, you had to get the friction factor. How are you going to get the friction factor? Moody diagram. From the Moody. If I jump back to that equation, it's right here. The Moody diagram to get that friction factor. And so let me do this to show you the results. Is if I come here and I say, what happens if it's a rough tube? Does it change my hydraulic diameter if I have a roughness for the walls of the duct? No, it doesn't change. How about the Reynolds number? Well, I went back to using this temp fluid all at 350, but it didn't change the Reynolds number. The Reynolds number is the same. It's 42,735. All right. So what about the friction factor? I have to calculate the friction factor from the Moody diagram. Do I have a Moody diagram anywhere? So the friction factor from the Moody diagram is 0.023. If you had a Moody diagram and you looked at it, that's reasonable. It's on the low end. It's not that rough. Okay. What did I do right here? Can you see that? What did I do right there? I used one approach, which is simply the modified Reynolds analogy. The modified Reynolds analogy gives me a Nusselt number of 109. All right? If we use this correlation, I have a little more thumb work on my calculator, and I calculate 98.2. Tell me. Yeah, they're different. 109 versus 98.2. They're both okay. This one is the preferred approach at this point. All right, so now I get an H using the 109. Oh, I didn't use it. Went back and used that one from the modified Reynolds analogy. Get an H to then solve for the outlet air temperature of 41. What was my outlet air temperature before? 39 and 41 are pretty close. Well, with that, we covered what we wanted to cover in internal flow. I wish I had more time to solve more problems. I encourage you, you just have to solve problems. Hopefully I've given you a good roadmap and hopefully you're not too confused about this chapter. But this chapter, if you're going to take that FE exam, and there's sections on the FE exam that deal with heat transfer, as well as fluid flow, this would be an important chapter to review for the FE exam as well as to pass this class. Thank you for your attention. We're done.